Welcome again to the glass plate. In this example we're going to take a look at a rod in which heat is conducted away to the sides, but inside the rod there's internal heat production. And we're going to analyze in a steady state what the temperature profile inside the rod will be. Let's start with a sketch. This is the rod of length L. You may think of it as just a cylindrical shaped rod. At the ends it is held at a fixed temperature T0, same on both sides. Inside, production takes place in a uniform way, and I'll denote that by Q with 3 dashes. This is production per unit volume, or per cubic meter if you want. Everywhere inside this rod there is this heat produced, so in every cubic centimeter the same amount is produced. We will further assume that this rod is insulated all around, except for the two ends where it's fixed in temperature. This means that the heat produced inside can only escape left or right, and this turns it into a one-dimensional problem which is relatively easy to trace. We will need a coordinate system, and we'll call this side x equals 0, so x runs in that direction, and then obviously this side is x equals L. And I would like to know what the temperature is. Before we do anything, we can anticipate qualitatively what will happen. All heat produced will heat up the temperature of the rod and will increase it, and the heat will flow to the sides. And as this is pure conduction, there is a lambda which is the same throughout the entire rod. It is heat flow via Fourier's law. And thus, as the heat has to go from the internal parts to both outsides, we can easily understand that the internal parts need to be warmer than the outside parts due to the description we know from Fourier's law. It flows downhill, hot to cold, hot to cold. And thus I can also anticipate that the hottest point will be exactly in the center. And then it goes downhill left and right. But we can compute that. And we can find out that it will be a parabola. How do I do it? Well, it starts with realizing that we need a heat balance. And in steady state, the heat balance read, as we know, 0 equals in minus out plus production. But I have to specify first, before I can use this any further, a control volume. Now it's not a good idea to use the entire rod as the control volume, because how on earth can I tell then that it's hotter on the inside than closer to the walls? To find out what the distribution is, I need to look at an arbitrary small part out of the rod that is situated between x and x plus dx. And I'm going to consider this part, and only this part. But I didn't tell you where it is, and I don't want to tell you where it is, because it can be placed anywhere. I keep it generic. But I can set up my balance, and if I draw this part out, then it has heat coming in, going out, and there is production. Although I realize that on the left side probably the heat will go in the other direction. But I don't have to specify it. This is how I can imagine it. Heat is flowing from left to right, and if it turns out the other way around, the signs will automatically flip in my analysis. So I keep it as generic as I can. And thus I can write down that this arrow, the inflow, equals the area of the rod. Think of it as a circle. The area, let me draw it. This area, it's a cylinder. It comes in through these areas, so this is also circular in shape, area A, times the heat flow, which according to Fourier, the flux is minus lambda, the T, the x. But I need to be careful, this is inflow at position x. Outflow is the same. That is to say, it's the same in its formula. But whether numerically it's the same is to be seen, because I need to evaluate this at position slightly to the right, x plus dx. It doesn't say that these two are the same. can be higher here than there, or the other way around. Then finally I need to give the production. Well, the production is equal to the production of heat per unit volume times the volume that I have. And my total volume is the area A, times the thickness of that small piece that I took out. A dx is the volume of this, the volume that I marked here. Multiply that volume by the production per unit volume and you have the production in this volume. Okay, this looks pretty complicated and let's sort out this a little bit. First, we see that we can scratch out the A as that is in all terms. Second, we see that this minus sign and this minus sign turn this into a plus. So if I rewrite this equation starting with this term and the 0 on the right hand side, so we flip the equation, then it starts with lambda dt dx taken at x plus dx, that is the out term with the double minus sign, and then the in term has a single minus sign, so I subtract that, minus lambda dt dx done at position x, plus q with 3 dashes dx equals 0. This is the steady state balance for this problem. And this looks complicated, and it is more complicated than we've seen so far. But I can make this somewhat simpler. I can write this as dt dx at position x plus dx minus dt dx at position x, that is this term except for the lambda, and I divide this entire equation by dx. So I divide by dx. And then I move this term to the other side, that gets q with 3 dashes, no more dx, because that is over here, and I shouldn't forget the lambda, which is now below. Okay, this might look awfully complicated, but in fact if I look mathematically what is written, it is some function taken at x plus ds minus the same function at x divided by dx. That is the derivative of that function. But that function itself is already dt dx. If you find this complicated, read for this, and I'll write it in black, some function f, and for this, the same function f. So now it's f at x plus dx minus f at x divided by dx. But that's the derivative of f. So this term becomes the derivative of x with respect to x, which is, as f itself is the derivative of t, the second derivative of t with respect to x, and that equals minus q1 to 3 over lambda. And here is the differential equation that we need to solve. Looks pretty nasty. But it's not too bad. I can integrate this once. If I do that, I get dt dx, because this is the second derivative, is the integral with respect to x of this term, but that's a constant, so this becomes q1 to 3 over lambda times x, plus, I shouldn't forget, some integration constant. Alright, but I wasn't looking for dt dx, I was looking for t. So if I continue here, now I can integrate this with respect to x. Now I get t equals, I need to integrate this with respect to x. Integrating x gives me half x squared. So this term becomes minus q, 3 dashes over lambda, x squared over 2. Integrating c1 with respect to x gives me c1x, and I shouldn't forget that integration gives me another integration constant, c2. Here you have the general solution of this equation. But it has two unknown constants. How do I find them? Well, one is sitting here. At the left side, x equals 0, the temperature is 0. Is T0. If I put it in, T0 is dus, at x is 0, this is a 0, at x is 0, this is a 0, equals C2. So using this boundary condition, at x equals 0, the temperature is fixed T0. This line gives me then this term equals T0. This gives a 0 contribution at x equals 0, and so does this one, and thus T0 equals C2. I have a second one on the other side. At x equals L, This should also be t0. If I substitute that, I get t0 equals something that I need to compute plus t0, such that something that I need to compute is in itself 0. The t0 here, if I put in at XSL temperatures t equals 0, that temperature here is exactly cancelled by our C2 that we already had. So the second one gives me minus Q3 dashes lambda L squared, because at XSL I know that, over 2 plus C1 times L equals 0 as these two cancel, and thus I can back out C1, which is plus Q3 dashes over 2 lambda and 1L, as I can scratch out 1. So now I have my full solution. I can substitute these, and you see that T equals T naught plus, if you combine this, a parabola in X. I'll give you the final solution here. I can just scribble it under. T equals T0 plus, if I combine this into a parabola shape, Q1, 2, 3 dashes over 2 lambda times Lx minus x squared. This is the exact solution of the temperature difference. Check for yourself that this parabola has a maximum at x equals L over 2, as we expect based on symmetry. This middle point should be the hottest. Pretty tough mathematical question. Bottom line, one that we can follow with what we've been doing. I've been setting up, via the drawing, a balance over a small part because I like to find the temperature distribution. Not the temperature, but the distribution. Colder here, hot in the center. If I look at this, steady state, 0 is in, minus out, plus production. Production is the amount of heat per unit volume produced times the total volume, just the volume that I had in mind, my control volume. Inflows through the area A, the cross-sectional area, Fourier's flux. Out flows the same formula, but these are evaluated at different places. Left and right don't have the same gradient. Once you have done this, the rest is mathematics and boundary conditions. This is complicated in itself, true, but if you look up in textbook and calculus books how to do it, you will find out that indeed what I did is a way to solve it. For our course, the bottom line is, can you set this part up? Can you arrive at an equation like this? If you can, great job. If you have difficulties following it, look it up again and try it yourself.